Okay, so let's see what is Werner's experiment. Okay, so how did he find the structure of these coordination compounds? Okay, so before he start his experiment, he knew that this is the formula of the compound. Okay, uh, they knew the formula, but then they didn't know the structure. That is, how these three chloride ions and these ammonia molecules are bonded to this cobalt. They didn't know the structure. Okay, so Alfred Werner was a person who found the structure of these compounds by doing an experiment. Okay, so let's see what is his experiment. What he did was he took a series of compounds which contains three things in common. Okay, one was cobalt, a metal ion, cobalt ion, and then NH3, and the other one was Cl minus. Okay, so he took four compounds in which these three ions were present. Okay, so these are the four compounds which is given here. Okay, these four compounds were different in their colors. Okay, so COCl3 dot 6NH3 was yellow in color, COCl3 dot 5NH3 was purple in color, and these two, if you see, the formulas are same, but you see the colors are different. One is green and one is violet. Okay, so these two are isomers, they have same formula. Okay, so he took these four compounds. Okay, and you know what he did? He added silver nitrate solution to these four compounds. Okay, so what happened was, in your first year, you would have done confirmatory test for chloride ion, right? What did you do? You took the solution of salt and then you added AgNO3 to that. So when you took the solution and when you added AgNO3, what happened? You got a white color PPT, right? So what was this white color PPT? This white color PPT which you saw was silver chloride, AgCl. Okay, so now even here, these are all these compounds contain chloride, right? To this, when you add silver nitrate, you will get AgCl. Okay, now in this particular experiment, there is difference in the number of moles of AgCl precipitated. Okay, so if you see, in all these complexes there are 3 Cl. Okay, but then you see the number of moles of AgCl precipitated is different. Okay, so why is it different? So what is different in all these four complexes? Okay, so as I told you, in a coordination complex, if you have CO, NH3, 6, 3Cl, okay, then I told you the part which is there inside the square bracket will not dissociate. Even if you dissolve it in solution, this bond is not going to be broken. Okay, only this part will be broken. Okay, and you will get 3Cl minus ions. Okay, so if it was this complex, then these 3Cl minus will dissociate and you will get 3 moles of AgCl. Okay, now, so that was this first complex which you see. Okay, now you look at the second complex. It is COCl NH3 5 times square bracket 2Cl. In this case, you see there is one Cl which is there inside the square bracket. So this Cl cannot be precipitated. It cannot be dissociated from this complex. So you have only 2 Cl which is outside the complex. So only these 2 Cls can be dissociated and it can form 2 moles of AgCl. Okay, so that is how in second case, you see, you get only 2 moles. Okay, that is because you have only 2 Cl minus outside the bracket. Similarly, in the third case, you have 1 Cl minus which is outside the bracket. So you get only 1 mole of AgCl. In the fourth type, which is an isomer, you have only 1 Cl minus, so you'll have only 1 mole. So by doing this, he could tell that this is the structure of these complexes. Okay, and after doing this experiment, he gave several other terms. Okay, we'll learn all those now. while learning the postulates, we learn all those terms. Okay, so I hope you understood the experiment. So what he did was he took a series of compounds of cobalt, chloride and ammonia, and then what he did was he added silver nitrate solution to that. So when he added silver nitrate solution, it gave silver chloride. Okay, so the silver chloride which was precipitated was in different amounts. Okay, that is because of the difference in the formula. Okay, so before we learn Werner's postulates, let us go through the structure of coordination compounds. Okay, so this is an example of a coordination compound. So as I said, a coordination compound will contain a metal atom at the center, which will be surrounded by ligands. Okay, so these ligands can be anions or neutral molecules. Okay, so in this example, NH3 is a ligand, which is a neutral molecule. It has lone pairs in it. Another example can be H2O. It will have neutral molecules. Okay. In case of anions, it can be Cl minus or Cn minus. Okay, these are all examples of anionic ligands. Okay, so metal will be surrounded by ligands. Okay, and this is a coordination entity. Whatever is inside the bracket is a coordination entity. Outside the bracket, you will have a counter ion. Okay, so this is called a coordination compound because it has coordinate bond. Okay, so this bond between the metal and the ligand is a coordinate bond. Okay, so what's a coordinate bond? So covalent bond is nothing but sharing of electrons, right? So if you have HCl, hydrogen will contribute 1 electron and chlorine will contribute 1 electron. So this in this type of bond, both the atoms are contributing 1 electron. So this bond is nothing but covalent bond. Okay, but in case of coordinate bond, even here it is sharing of electrons, but then both the electrons are from one particular species. In this case, NH3 molecule, it has lone pairs. So these two electrons are being given to, it's been shared between both NH3 and cobalt. Okay, so this bond is known as coordinate bond. Okay, so always, so the ligands, it has to be neutral, which has lone pairs, or it has to be anions with negative charge, excess of electrons. Okay, so let us learn two more new terms. That is nothing but primary valence and secondary valence. Okay, so what is primary valence? Primary valence is nothing but the oxidation state of metal, and this oxidation state will be known to us. Okay, for example, in case of NaCl, okay, this will be +1. Okay, the oxidation state of sodium will be +1. Okay, and if it's FeCl2, oxidation state of Fe will be +2. Okay, so the oxidation state will be known to us. So there's a way to calculate the oxidation state of this metal. Okay, I'll teach you that. But in this case, the oxidation state is +3. Okay, so the primary valence of this particular complex is +3. Okay, and this primary valence is ionizable. Okay, so you can ionize this. So the primary valence is ionizable, and this is variable. Okay, it can be different. Example, Fe can have +2 or +3 state. Okay, in FeCl3, the oxidation state will be +3. Okay, so the primary valence is ionizable and it's variable. Now, moving on to secondary valence. Secondary valence is nothing but the coordination number of metal. So the coordination number of metal is nothing but the number of bonds it has. Okay, so in this case, it has 6 bonds with NH3, right? So the coordination number is 6. Okay, and this coordination number is non-ionizable. So why is it non-ionizable? So as I said, when you dissolve this complex in water, only this part of it is getting ionized. Whatever is inside the bracket will not get ionized. Okay, so that is why these 6 bonds will remain as it is. So that is why we tell it's non-ionizable. Okay, and the secondary valence is fixed to a given metal. Okay, so if you see the secondary valence of cobalt, that is coordination number of cobalt, in most of the cases it will be 6. Okay, and maybe for platinum in most of the cases it will be 4. Okay, so it is fixed to a given metal, whereas primary valency is variable. Okay, so the primary valence of this particular complex is +3, because that's the oxidation state of metal, and secondary valence of this complex is 6 because it has 6 bonds with NH3. Okay, so let's go through the postulates of Werner's theory. So the first postulate. The first postulate tells that metal can have two types of linkages or valences. Okay. So just now we discussed what are the two valences, that is primary and secondary. So this is your first postulate. Second postulate tells you what is a primary valency. Okay, so as I said, the primary valency is nothing but the oxidation state of metal. Okay, in this case, cobalt will have an oxidation state of +3. Okay, so that is the primary valence. Okay, so this primary valence are ionizable and satisfied by negative ions. Okay, so the +3 charge of this particular metal ion is being satisfied by negative ion, that is Cl minus. Okay, so that is your second postulate. So the third postulate tells you what is a secondary valence. Okay, secondary valence is non-ionizable. Okay, so what is secondary valence? Secondary valence is nothing but the coordination number. Okay, so in this complex the coordination number is 6. Cobalt has been bonded to 6 ammonia molecules, so the coordination number is 6. So this secondary valence are satisfied by neutral molecules or negative ions. So these neutral molecules or negative ions are nothing but the ligands. In this case, the ligands are neutral. Okay, NH3, as you all know, has a lone pair of electron. So this lone pair of electron is being donated to cobalt metal. Okay, so the secondary valences are non-ionizable. So whatever is there inside this particular square bracket cannot be broken. Okay, so this is non-ionizable and are satisfied by neutral molecules or negative ions. It is equal to the coordination number. So the secondary valence for the cobalt is 6, and it is fixed for a metal. Okay, so for cobalt, if you see, the oxidation number will be 6 in most of its complex. Similarly, platinum will have a coordination number of 4. Next, the fourth postulate. Ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangement corresponding to different coordination number. Okay, so this tells about the shape of different complexes. Okay, so if the coordination number is 4, the shape of the complex can be tetrahedral or square planar. Okay, if it's 6, the arrangement will be octahedral. Okay, so this secondary linkages is nothing but the coordination number. Okay, will have characteristic spatial arrangement corresponding to different coordination number. So as I said, different coordination number will have different spatial arrangement. Okay, and this type of spatial arrangement is called coordination polyhedra. So these are the 4 postulates of coordination compounds which are proposed by Alfred Werner. Okay, so the first one tells you that there are two valences, that is primary and secondary. Second postulate tells you what is a primary valency and how is it satisfied. Third postulate tells you what is a secondary valence, and the fourth postulate tells you about the coordination number and spatial arrangement. Okay, so you'll have to know the 4 postulates of Werner's theory. It's a very important question. It's a 3 marker. Okay, so let's quickly go through the topics what was done today. Okay, so we learned what's a coordination compound. Okay, and the difference between a double salt and a complex salt. So you learn one example from double salt. Write this in your notes. Okay, and the experiment done by Werner, you can just go through it. Okay, then yeah, then the postulates. Okay, postulates are very important. It's a 3 marker. Okay, learn all the 4 postulates and write all the 4 postulates in your notes. Okay, so we'll continue the chapter next week. Okay, next week we'll be doing some of the terms which you already know by now. We'll learn what is a coordination entity, what is a ligand, what is a central atom, what is coordination number. Okay, once again we'll go through all this. Okay, so revise whatever is done today. Okay, and be ready for your next class. Thank you.